So welcome to our virtual astronomy class this week. We're going to be talking about light and telescopes. Before I get started, does anybody have any questions they would like to ask? Either type in chat or over your microphone. Okay, good. I will, when I share my screen on the PowerPoint, I will not be able to see the chat. So if I say something you don't understand, you're welcome to interrupt me with your microphone, if you have one. If not, you can type your questions in chat and I will answer them after the presentation. So let's get on with the show. All right, and here we go. So as I said, we are going to talk about light and telescopes. This presentation will just be on the light part of that, the nature of light. I have a recorded lecture that I gave last semester about telescopes. I kind of alternate back and forth on which to give live. And so you can see the recording lecture on telescopes. Let's talk about what light is. Now, you've already answered, most of you already answered our discussion question and you've done the reading. And so you have a better idea of what light is now, probably than what you had before. But let's think about how we experience light and what we thought about as light before. I've always thought of light as particles. Now I'm a particle physicist, so I guess that's kind of natural. But before I was a trained physicist, I thought of them as little bundles of energy, and that's certainly that remains a valid way to think of light. But we learned last week with Maxwell's equations, the thing that got Einstein started on the theory of relativity. Much like wave, we transfer information through that. We think of light as being invisible, but that's mostly because there are there's lots of invisible light, but even visible light, in the daytime at least, we don't see it in action. We experience it. We know if we turn off the lights in a room that it goes dark. But when we turn the light on, we don't see anything coming out of the light bulb. It's like instantaneous. Trying to figure that out. Now, at nighttime, you might be able to see beams of light. When you turn on a flashlight, when it's completely dark, you can kind of see. You can kind of understand that it's localized. That you can have beams from a spotlight or the sun shining through the clouds. You can see different aspects of light. And so we're going to kind of put some science behind that. It's incredibly important for us to understand light and the importance of it. Beyond gravity, we will use gravity a lot to understand the universe, to explore the universe. We can see how objects rotate around each other, and that will give us an idea of what their masses are. But besides studying orbits and studying gravitational effects, what we're left with is looking at the light from the universe. And so most of it, and it goes beyond just looking at pretty pictures. By the end of this lecture, you'll know all of the different things that we can discover about an object just by analyzing the light that is either reflecting off of it or passes through its atmosphere or it's emitting. Let's go down to the basics of visible light anyway. what you may not have known is that visible light, this white color, so the light from the sun is actually white. If I put it through a piece of glass with a certain geometry, or a piece of plastic with some geometry, I can separate out, we would say, the different colors. This is called a prism. It was actually first studied by our old friend Isaac Newton, by the way. Isaac Newton thought of light as being particles. This was before Maxwell. And so before Maxwell, most people thought of light as being, tiny little invisible particles that were moving. The prism kind of breaks up this white light from the sun into its different colors, we would say. What I would say, and what you'll say from now on, is we don't really talk about colors. We talk about those are different energies of light. Those are different wavelengths of light. Those are different frequencies of light. Those are the way we specify different kinds of light, not by their color, because there's all sorts of different kind of light that's not visible to us. It has nothing to do with colors. But the colors of the rainbow, or the colors that come out of a prism, are just different energies of light. So what is light? Maxwell would tell us that light is an electromagnetic wave. What does that mean? Well, I assume you've heard of the electric force before. That's what's electricity in your house. That's what actually powers the lights that we see. Magnetism, your refrigerator magnets, the magnetic field of the earth, you're familiar with, even if you don't realize it. That's how a compass works. What Maxwell demonstrated was that electricity and magnetism are really the same force of nature, called electromagnetism, and you can't really have one without the other if anything is moving. You can have an electric field that's not moving, or a magnetic field that's not moving, but once you move any of that, they actually feed on one another, and a changing electric field will produce a magnetic field. A changing magnetic field will produce an electric field. Very much like if you drop some water in a tub, you would actually see these ripples, these waves. So it's the same kind of it's the same phenomena, except for one very important difference, in that water waves and sound waves, by the way, require a material to pass through. Right? You can't talk in outer space because there's no air. Sound waves are really just the air molecules either moving up and down, or kind of compressing and decompressing. Same way with water waves. Actually, you can't see it. You're used to the wave going up and down, but actually the material gets compressed and released. But they need material to propagate through. Electromagnetic waves, however, do not. They propagate through empty space, through vacuum, through air, through glass, actually. They don't propagate through all materials. They won't go through metals, by the way, but they don't need a media to travel through. They can travel through vacuum. This is what that looks like in kind of animated terms. It kind of looks like water waves coming at you, but in the perpendicular direction, we have the magnetic field. They kind of peak together, and they go to zero together, and they go negative together. They're highly correlated with one another, and this whole this bundle of energy, this electromagnetic force, propagates through space, and it propagates through space at the speed of light. This was the fundamental principle that Einstein's theory of relativity was based on. It actually came from Maxwell, that light travels at the speed of light. It's kind of weird, right? It's like having a car. It can only go 100 miles an hour. It can never slow down. It can never speed up. That's the weirdness of the particle of light, or the wavelength of the propagation speed of the waves. Right? It's like the ocean or Lake Michigan. The waves come at different speeds depending on the wind, right? But not with light. It's always exactly the same speed, which is weird in itself. So how do we describe, let's talk about light with its wave properties. How do we describe those wave properties? One is the amplitude, how high the waves are. Think the ocean again, how high the waves are. That's the amplitude. We don't actually use that much in astronomy. If you become an electrical engineer, or maybe even in your film career, you might when you're transmitting signals, this is what's important. The higher the amplitude is, the more power it has, the longer distance it can travel. But we're not going to worry about that. Travel through clouds and things. We're talking about light that travels through empty space. And by the way, we've learned light can travel through billions of light years, over billions of years. We see the light. The light is not disturbed. It can travel through empty space, and nothing is going to affect it. If it hits a cloud or something, we're going to talk about what happens. It actually, some of it will go through, and it gives us some extra little bit of information with that. Another way to specify a wave is the wavelength, either the distance between the peaks of the wave. And it's going to be measured in our new favorite unit. It's going to be measured in meters, but most light doesn't have wavelengths of meters. It will be nanometers or even kilometers. So if you're not caught up on your Greek prefixes, right? K means 1,000. Nano or a little n means 10 to the minus 9. Look in the formula sheet or the appendix in your book. That's how we're going to specify the wavelength of light. And when we do our equations, our math equations, we have to make sure that we're using meters. And if it's nanometers, we have to use our scientific notation. For instance, if it was light of 1 nanometer and we plugged it into equation, we wouldn't put 1. We put 1 times 10 to the minus 9, because that's what the nano stands for. In general, waves have a speed, which is kind of the speed at which these crests or the troughs, doesn't matter, they all go at the same speed, hits you. But for light, that speed again is always constant. It doesn't change with the wind as water does. The other way we specify light is, or another way, is the frequency. The frequency. Now you're used to thinking of frequency when you tune on your radio, and hopefully by now you know that radio waves are just like visible light waves. They're all electromagnetic radiation. So when you turn that dial to 101 or whatever you tune to, that's the frequency of the radio station that you're listening to. That is just how many of those peaks hit you per second. That's what the frequency is. If you'd like a visual of this, I encourage you to click on this. This is in the PDF. This Astro Tour is a little kind of guided video that'll actually show you these waves in action. It actually has a little kind of quiz built into it. It's not required, but if you're having a hard time understanding this, it can kind of help you out visually, with the waves actually moving. So we have several important equations in this chapter, and one of them relates the wavelength and frequency to the speed of light. The symbol we use for wavelength is this Greek lambda. The symbol we use for frequency is f. And remember, the speed of light is so special, it has its own symbol for it. C, 3 times 10 to the 8th meters per second. That's the speed of light we're going to use in this chapter. Remember, we also have a 1 light year per year, but when we're talking about using this equation, we're not going to want to use that for our speed. We're going to use this for our speed of light. 3 times 10 to the 8th meters per second. That's 3 with 8 zeros behind it. tremendously fast. And as Einstein told us, no object can travel through space-time faster than that. We'll learn later on in this course that the universe itself is expanding in some places faster than that, but nothing can travel through space and time faster than the speed of light. So let's reconcile Newton and Maxwell, and we'll throw Einstein in because he's the one who's going to tell us how this relates to the energy. How do we reconcile these two different ways of thinking about light? We don't actually. Light and tiny objects, and actually all objects, have what's called wave-particle duality, which means they have aspects of them that behave like a particle. They have aspects of them that behave like a wave. And so a wave property is something that can interfere with another wave. Like if you're at a concert, sometimes you can't quite hear the speakers because they're out of phase with one another. Or if you see light get bent across a window, or if you look through a piece of glass that's a little bent, you can actually see the distortion. Those are wave properties. You can see that on the ocean where there's a wave break, right? And you have a little opening in it. You'll actually see kind of this round pattern as the water goes through it. It's kind of like the wave fronts get bent. That's kind of the wave part of it. You can imagine if you had, well, you do. You don't have to imagine it. It's hard to imagine because it's so tiny. You actually have a wave property associated with you. It turns out that this is a quantum mechanical approach to matter. Every particle, every piece of matter has a wavelength, but it's smaller the more massive the object is. So we're talking, we said last week we're talking about how much more massive the Earth is compared to us, but we're a lot more massive compared to the mass of an electron, for instance, on even a larger scale. We're more massive. The difference between our mass and electrons is greater than the difference between our mass and the sun's, actually. There's more order of magnitudes going down than there is going up. So our wavelengths are incredibly tiny. But if we shrunk ourselves down to the mass of an electron, it would be like we had these kind of invisible butterfly wings. But when we tried to walk through a door, those wings would kind of get caught on the edge of the door, and it might turn us around. If the wings were too big, they might not even let us get through. So that's we actually see this for electrons. We see this for atoms. About up to the size, or smaller than the size of a carbon atom. Everything that's more massive than a carbon atom, the little wings, the wavelength that's associated with them are basically inside the object themselves, so you don't really notice them. So this wave particle duality is not particular to light. It happens for every tiny particle, and light is the smallest and it's the lowest mass particle that we know of. In fact, it's massless. It has zero mass to it whatsoever. The particle associated with light is actually called the photon. So if you Star Trek fans remember the photon torpedoes, they were shooting torpedoes of light. And so you can kind of think of a little water droplet, instead of hitting the surface of the water and making waves, the water droplet's causing these ripples in space-time. It's not really ripples in space-time, right? It's not gravitational waves, but it's ripples in the electromagnetic field as it kind of moves up and down, or just drops or whatever. This is our introduction to the weird world of quantum physics, which was really understood by Einstein. Again, this is Einstein's, this is called Einstein's energy equation. It's not his famous one, E equals mc squared. This is E is equal to H, which is a constant of nature. It was named after a German physicist, Planck, who was trying to make a better light bulb, actually. And he was trying to design a more energetic light bulb. He realized that there was a bundle of light energy that he could not get below, which is kind of weird. We don't think of, you don't think of water as being quantized. Like you can kind of cut it up. If you're trying to cut up a carrot, right, you can cut up into different pieces, but then you can cut it up smaller and smaller and smaller. That's what, and unless you would think that, there's really not the smallest little bit of carrot that I could cut into, but it turns out there is. It's an atom, right? There's some part where you actually can't break apart. Even if you can break apart the atom, it's going to have tinier things in it. There's a tiny little piece of matter, which are electrons or quarks, that you can't get beyond. You can't cut those up. The same thing goes with light. Even though, especially if you think of light as a wave, it's like, well, come on, how can there be a tiniest little piece of wave? But there is, and it's called Planck's constant. It is really the fundamental piece of energy, the tiniest little slice of energy that you actually you can't cut it in half anymore. This is Einstein working off Planck came up with this equation. The energy of a photon is equal to Planck's constant times the frequency of a photon. And you'll see that the frequency, the Planck's constant is an incredibly tiny number. This EV stands for an electron volt. It's a tiny amount of energy already. And then the Planck's constant is 10 to the minus 15th of those. So a single photon of light, even from the sun, right? You can go out and you can feel the sun's energy on your skin. But that's not from a single particle of light. A single particle of light you would never even notice. You wouldn't see it. You need very sophisticated technology to actually observe a single particle of light. We can do that, but our eyes can't. And you wouldn't feel it. It's a tiny amount of energy, but the light from the sun is trillions upon trillions of these photons that are hitting us, and that's what makes us feel warm. And an electron volt is tiny compared to a calorie, right? A calorie is probably the form of the unit of energy that you're used to. This is already like 10 to the minus 19 calories. So it's an incredibly tiny amount of individual bunch of energy. But if I put a bunch of them together, I can get a lot of money in my analogy here, right? I could get $1 million worth of pennies if I want. So that's kind of like the light from the sun is a bunch of these pennies hitting us. But again, the different colors of the visible part of the spectrum have different energies, and we'll learn that the different X-rays have higher energy than radio waves. And so you can have a little. You don't need as many quarters to get $25 as you do pennies. You can have the same total intensity or amount of energy per second. You just need less of it with the more energetic light there. And yes, this may seem counterintuitive to you because in English we talk about things being red hot, right? So you may think, many people think that the blue part of the visible spectrum is lower energy than the red part, but it's exactly the opposite. We'll talk about why we say things are red hot in a minute. Well, let's talk about it now, actually. When you heat something up, it gets redder and redder. It turns out if you kept on heating it, it would turn yellow and green and blue. Now, you don't see that because most things that you heat up they melt and they change their phase or they evaporate before they can actually start to emit these different colors of light. But for instance, if you're burning gas on your stove, you'll notice some of it's yellow, some of it's blue. If you've got a little blowtorch, if you're sweating pipes or whatever, you want to use the blue part of the flame. That's the hottest part of the flame. So the violet is actually the highest energy. The red is the lowest energy. And so we've got these relationships. Remember, the wavelength and the frequency are inversely related to one another. And now the energy is proportional to the frequency. So you can imagine you've got a third equation that relates energy to wavelength as well. Energy is equal to hc divided by lambda. So the higher the frequency, the higher the energy. The bigger the wavelength, the lower the energy, because the frequency and the wavelength are inversely proportional to it. So examples with visible light is red has the longest wavelength, the visible light, and the lowest energy. The violet has the shortest wavelength and therefore the largest energy and frequency. This would be the lowest energy and the lowest frequency of visible light. But that's not the only kind of light there is. Electromagnetic radiation comes in many forms. You've probably heard of all of these, and you may not have realized before this week that they're actually all the same stuff. They're all electromagnetic radiation. Let's go from the lowest energy, the radio waves, which is what we transmit information. TV waves are the same kind of thing. We don't really separate those out. The microwaves, your microwave oven, your mobile phones run on microwaves. Infrared light. This is the light that you actually emit. You are emitting light right now. It's just not visible light. Some people call this thermal radiation or heat light. Any object that is warm emits some kind of light. The sun is incredibly hot. It emits visible light. The Earth and people aren't that hot. We emit infrared light. This is Navy SEAL goggle light. This is night vision goggles. That's how they can see heat signatures. There's our old friend visible light. And then you've heard of ultraviolet light. This is the stuff that you have to wear sunscreen to keep from burning. That's actually kind of the lowest energy ultraviolet light. We'll learn in a couple of weeks that our atmosphere protects us from the worst part of that. X-rays, the stuff that you take pictures of your bones and teeth with, and gamma rays, the stuff that made the Incredible Hulk green. Or in the real world, this stuff is produced in nuclear reactions. It's produced in astronomy by the most cataclysmic explosions and collisions in the universe actually produce gamma rays. So we can determine the temperature of an object by the amount of light it emits. Remember, temperature is just kind of how fast the particles are moving, how much kinetic energy on the subatomic, on the atomic level, not the subatomic, on the atomic level, how fast those particles are moving. That's really what temperature is. When you touch something that's hot, that means its molecules are moving faster than the molecules in your hand. If you touch something cold, that means they're moving slower than the molecules in your hand. The stars are hot enough to emit visible light. We'll learn that there are blue stars that are much more hot or have a higher temperature than the red stars. And planets emit infrared light. This follows a law. This was discovered by a German physicist named Wien, and this is Wien's law. He noticed he noticed this relationship between the temperature and the wavelength, color, if you will, but it's not just visible light, the wavelength of the light that it emits. So the hotter an object is, so first off, the hotter an object is, the brighter, the more intense the light will be. It'll throw out more photons per second than something that's cooler. But not just more light, but the wavelength will be different. The cooler it is, the more red it goes. On the other side of the visible spectrum, we have the infrared spectrum. We have things that emit microwaves. So here's Wien's law again, just kind of showing you the variation with different temperatures, how much more intense the light is, and the peak, it still emits, right? Our sun emits all of the colors of the rainbow. That's not by coincidence. Rainbows are caused by the light from the sun. It's also not a coincidence that this is what our eyes have evolved to see. We've evolved to see the light, the most prominent light from our sun. We can relate this with some, it's not very tricky math, it's easy math, but we got to be careful with the constants in here. And what we mean by lambda max. Lambda max is, if you looked at all of the light, which wavelength would have the most intense? Which wavelength or which energy photons are being emitted mostly? It's a spectrum, right? I mean spectrum. It's not all one color. It's not all one energy. It's a spectrum. But this tells us where this point peaks. It's related to temperature. But it's not temperature that you're probably familiar with unless you've taken either an astronomy class before or a chemistry class. And it's not Celsius. I'm not talking about Celsius temperature. I'm talking about Kelvin temperature. We talked about it a little bit in our laws of the universe, right? This corresponds to no motion of particles. 0 degrees Kelvin, actually, our law of thermodynamics says we can't get to actual 0 degree Kelvin. Absolute zero is impossible to get to, but we can get close. But that's that temperature. It's minus 273 degrees Kelvin. Celsius is 0 degrees Kelvin. So that's what we're going to be measuring our temperatures of our planets and our stars in, because that's what we get out of looking at the light from them. We can actually tell what their temperature is. We'll do more examples of this as we use the. I mean, there'll be some examples now, but we'll use it again and again and again when we look at the different temperatures of different objects. Here's just our visible part of the spectrum related to the other categories of light. Again, you don't need to kind of do these subcategories. We just call all of this stuff radio waves, TV, FM, radio, AM. These are all radio waves, microwaves, infrared. You can kind of see how the wavelength kind of changes, right? The distance between the peaks changes. I don't expect you to know any of these numbers except for the ones on visible light, and you don't need to know the differences. You just need to know that visible light is between 350 nanometers and 750 nanometers wavelength, and it's the tiniest part of the overall spectrum. The other thing I want you to know is the energy, right? I want you to know that gamma rays are the more energetic and radio waves. You need to know the whole, you need to be able to tell me the different categories of electromagnetic radiation going from the lowest to the highest, or from the highest to the lowest. What do we use that for? We already talked about how we use it for ourselves in the real world. But what do we do that in astronomy? And this kind of, up here, it kind of shows you something you might be familiar with, the wavelength. Like some of these things have wavelengths the size of a football field. Some of them have wavelengths the size of a hydrogen atom. You may not know what that is, or maybe a protein inside of you, or a bacterium. But what do we use these in astronomy for? Let's go from the highest energy. These are gamma ray bursts from collisions of black holes or matter that's getting super hot around a supermassive black hole, or single star black holes emit X-rays. Neutron stars emit X-rays. Our sun emits mostly visible light, a little bit of ultraviolet light. Infrared light is for the planets and the cloud forming, the giant clouds of dust and gas where the planets are forming. The Big Bang, we actually can listen to the afterglow of the Big Bang. It's still out in the universe. It's cooled down, or it started out about the same wavelength or energy as the surface of a sun. But now it's cooled down to a microwave energy. And then the the giant, the dust and gas that's cool, that's not making stars, it's just kind of in between, the spiral arms of galaxies, for instance, they actually emit radio waves. So we use all these kinds of different kinds of light, not just visible light, to study astronomical objects. So let's talk about how light interacts with matter. It can reflect like in a mirror. It can get bent like in your glasses. It can scatter kind of like pool balls, hitting particles in the sun or particles in our atmosphere. Things can get absorbed. That's why things have different colors. If you get something hot, it'll emit light, or it can go through, right? It goes through like glass pretty easily. It can just go right through. It doesn't lose energy. It loses a little intensity, but not a lot. Or we call that transparent objects, just allow light to go through it. But we also have opaque objects that don't allow any light to go through whatsoever. And these can have very different percentages, right? On a cloudy day, it's not completely dark, so clouds aren't really transparent or 100% transparent or 100% opaque. They're kind of in between there. So let's talk about spectroscopy. What happens when light goes through, let's say, a cloud of dust or gas? Let's think of the light from a star, and let's say it's hitting us without going through anything, just going through empty space. This is what we started today's lecture with. We have white light from the sun. It goes through. We put it through a prism, and we can break out all of the different colors of the rainbow. And really, we have prisms that can separate ultraviolet light. We can X-ray diffraction. We can do this with any kind of light. Let's just talk about visible for a second. So that's what we call a continuous spectrum, all the different colors of the rainbow. Well, what if instead of coming straight to our detector or our eye, it went through a cloud of dust and gas? There's lots of dust and gas in the universe, so it passes through that, and it's so much that we actually very rarely actually observe this. This is what we actually observe. We almost see in a continuous spectrum, but it's got these little dark patches in it. This is called an absorption line spectrum. This is where that cloud of dust and gas actually absorbs some of that light. And it's very peculiar about the energy of light that it wants to absorb. It just only absorbs certain energies to that. And so it turns out this is kind of a fingerprint of the gas. Different molecules have different absorption line spectra. They all have, these are in different places. They have different numbers. They're really a way we identify objects, or what the composition of gas in the universe. Now let's look in a different direction of that same kind of cloud of gas. But we're not looking at the light of the sun going through it. We're looking in a different direction. We'll actually kind of see. We'll see this light that's in the same wavelength of the light that was absorbed. So this is when that same cloud of dust and gas gets hot. It emits light. As it cools back down, it emits light with the same energy that it absorbed. So that we call this an emission line spectrum. So hot gas will actually emit light. Cool gas that you're looking at a star through will absorb light. For instance, here's the Orion Nebula. One of the reasons I know that this is made out of hydrogen is by looking at this light. This is emitting. This red and this purple are actually indications of hydrogen. So that's how I know what this nebula is actually made out of. To really understand that, we need to understand atoms and how they work. Atoms are not like little marbles that you might think of. They're not like little planets orbiting around a tinier nucleus like you were taught in chemistry class. They're much more complicated than that. These electrons in an atom also exhibit wave properties. So an atom is really a very, very tiny nucleus that's made of the protons and the neutrons that is surrounded by this wave of electron energy. And this may look like, you might say, oh, this is an atom that has, I don't know, 100,000 electrons in it, each one of those little dots. But no, atoms only have the same amount of electrons as they do protons. So in this case, we have, what does it say? The red are the protons. So we have 4 protons that I can see anyway. There might be a 5th one behind there, but let's just say that there's 4 protons. That means that this is an electron cloud of just 4 electrons. But because their butterfly wings are so large, they really act like a balloon, like an energy balloon. This is what 4 electrons look like. They're not orbiting around. They are everywhere at the same time. This is the wave property of an electron. They are moving incredibly fast, but their presence it's more like just think of it as a giant energy wave, and it is giant compared to the nucleus. In order for you to actually see a nucleus compared to the effective size of this energy field from an atom, you would have to blow up the atom to the size of your favorite baseball stadium, and then the nucleus, the protons and the neutrons would be the size of a mosquito. In mathematics, that is 100,000 times smaller. The nucleus is 100,000 times smaller than this energy field. And to blow your mind even more, maybe, I don't know, the electrons are even smaller than the nucleus, even though they act like they're making this, their energy is as large as that the baseball stadium, relatively speaking. This is, of course, incredibly tiny. You could take 10 millions of those on the end of that black dot. There's 10 million electrons in there, or atoms in there. But the nucleuses are even smaller. The electrons, however, even though they seem that they can be everywhere at the same time, they have rules on where they can actually be. They have what called energy levels. We're going to skip this stuff. The energy levels, you may have learned this as orbitals in chemistry class. I mean, it's fine. It's a classical way of thinking of it. And chemistry kind of tries to melt the classical physics and quantum mechanics into something you can understand. That's fine. But we need to go a little bit beyond that to understand how light interacts with these atoms. So it's not, these are like different energy levels. These are like weird kind of steps. This is hydrogen. This is the effective cloud for just 1 electron and around 1 proton. So you can see it has these very cool different shapes that are energy levels here. And it cannot go. An electron or an atom, a hydrogen atom, can either be in this state or this state or that state. There's no in between, right? I can't, you can imagine, I got something that kind of halfway in between here and here. It won't work. That's what we mean by quanta. There's a level that you can't get to, and that's why it only absorbs that certain color of light. It can only let me show you this. You can kind of think of these as little steps. Only they're like crazy house steps. They're not equal, and some of them are really close together, and some of them are far apart. And just like you can't stand in between 2 steps, right? You can't levitate in between 2 steps. You either have to be standing on this step or that step, and it's the same way for the electrons. And in order for them now, the analogy breaks down because, right, you just have to eat a candy bar or some food, and you can run up as many flights of steps as you want. There's no one-to-one relationship to the amount of energy that you have to eat to go up a step, but there is for the photon or the electron. A little electron down here, if it sees some light with a certain amount of energy, let's say it saw a light that would get it up to here, you might say, oh, I'll take that one and then take another one next. It won't. It will sit here and it'll wait until it finds just the right energy, and it'll jump up to this level. It doesn't just, it could, if it found one that had enough to go up here, it'd go up here. But there's no in between here. And that's where we get that chemical fingerprint. And then when it gets hot, one of our laws of the universe is everything wants to go back down to its lowest energy. So when it goes back down, it emits that light of exactly the same energy, and that's why we get the absorption spectrum and the emission spectrum. And each chemical has a different band, a different pattern here. So helium, for instance, looks like this. Sodium looks like this. These are the emission spectrums. This is neon that looks like that. Right, your sodium bulbs in the parking lots. That's why they look yellow. Your neon bulbs for your signs. That's why they use they can glow in this red. A real object has not just usually doesn't have just a couple of elements. It has more than one, and so you can kind of see these fingerprints get a little mashed together. It's a little difficult by our eyes to actually decipher this, and they did for a long time. They would try to figure this pattern recognition out by hand. You're trying to figure out this pattern. We do it with supercomputers now, and I put it to you that it's easier to actually decode this than it is a human thumbprint. And match them up to the proper chemicals. It's actually the same technology. So you may not want to thank us for that, but we gave that pattern recognition to the NSA. We used it to figure out absorption spectrum first, but it works matching up fingerprints now. Here's what a absorption spectrum looks like for a star. So you can see it's very, very complicated. This thing has 60 identified elements in it. So the light that comes from the surface of a star actually goes through the atmosphere of a star, and that atmosphere absorbs whatever chemicals are in that atmosphere, absorbs this. So this is what we know the atmospheres of the stars are made of. And the first one we did this one was from the sun, and that's actually how we discovered the element helium. Helium on Earth leaves the atmosphere, right? That's why our helium balloons fly out. It's trapped underground. We didn't know it existed until we started drilling for natural gas and things. We actually discovered this element by analyzing the spectrum from the sun, and we saw there's this one pattern that we don't have on Earth. Well, we do now, but we didn't. By the way, we've never found an element in any of the billions of stars that we've analyzed that we do not have on Earth. So when your sci-fi people talk about elements that don't occur on Earth, maybe not occur naturally on Earth, but have never been seen on Earth, that's not true. There's no such thing as alien chemistry as far as we know it. The molecules that we see from the distant galaxies are exactly the same elements that we have on Earth. You can bend light, as you know. A way to do that. You can scatter light. Think of light as being particles that are interacting with the particles in the atmosphere of the air, just kind of like a game of pool. But it's kind of a rigged game of pool. It turns out only the blue particles like to participate in that game, and the yellow particles and the orange and the red particles pass through our atmosphere. Our atmosphere is mostly nitrogen, by the way, not oxygen that we breathe. That's about 20% of our atmosphere. 80% of our atmosphere is nitrogen, and that's what's responsible for the way our sky looks is the nitrogen in our atmosphere. It only plays pool with the blue light, or vice versa. It's more like the blue light is the cue ball. So the blue light only plays pool with the nitrogen. The color of the light of the sun, as we said, if we use Wien's law, we'll see we get all of the different colors of the rainbow. It peaks in green, by the way, but when we add that all up together, it turns into white. But we all, when we're kids anyway, we think the light from the sun is yellow, right? But that's not the case. The light from the sun is white. Here's a picture from the ISS through a huge filter of what the light from the sun looks like. You can see the blue sky on Earth. You can see the white clouds. So something's going on here, and it's not nitrogen. Nitrogen is a clear gas. Also, you notice that in empty space, when there's no atmosphere at all, it's black. When you're not looking at the light from the sun, it's black. That's not what we see, at least in the daytime on Earth, right? We see the sky being blue. So let's talk about why all that is. Why you thought that the sun was yellow is because that's the only time you can safely look at it, is during a sunrise or a sunset. And yes, it does appear yellow during those times. But when it's way up in the sky, don't try to look at it, it's white. Again, this is a high filter. Don't even try to take this picture with your camera. You'll have this white spot on every photograph. Any other picture you take afterwards, it'll burn out those pixels. It may be black or it may be white. I don't know. Just don't do it. Don't find out. You don't want to waste your smartphone on that experiment. But you don't need to, because the clouds, the light is reflecting off the clouds, or if it's cold out, the light is reflecting off the snow. That's when you're truly seeing the light, the color of the sun. And again, there's no one frequency for that. It's kind of weird. White light is not really, it's not a single energy. It's adding up all of the different colors. And black light is the absence. So there's a frequency that's associated with red light. There's a frequency that's associated with purple light. There's not a frequency associated with white light. It's all the frequencies of the visible spectrum put together. And there's no frequency for black. It's the absence of any light. So let's think about why the sky appears blue. Well, we said that the blue light plays that game of pool. So if I'm looking out here where there's nothing, right? Again, don't look at the sun, but if you did, the light would come directly from it. It would be white. But now I'm looking at a direction here where the sun isn't. The rays from the sun are going this way, but the blue part of that light is playing pool, and it's getting scattered in all these random directions, and that's what hits our eyes and our dog's eyes, and that's why the sky looks blue when we're looking at when we're not looking at the clouds, or we're not looking directly at the sun. And it's the same thing as why it appears yellow at sunlight, is as that light's coming through us, the blue light gets scattered away, and we only see the yellow part that's left. And the closer and closer the sun gets to the horizon, the redder and redder the sun gets, because it's going through more of the atmosphere. Not that it's closer or further away, it's because when it's first starting to set, it's going through about 30 kilometers of sky, of air. But the light, when it's right before it goes over the horizon, is going through about 620 kilometers. So it has more of that blue light gets scattered away, and it becomes more and more red. So let's contrast that with the moon. The moon has no atmosphere, so it's like being out in space. Again, these are incredibly filtered. The light from the sun, the astronauts that were on the moon, they had to wear these shields that blocked out 90% of the light. Because on the daylight side, this is just incredibly bright, just from the reflection. It's like being in Antarctica. You have to wear dark glasses just to protect your eyes. But the sky in Antarctica, the sky is not black. It's white. It's blue. But on the moon, you don't see any sky at all, because there's no atmosphere. Nothing to scatter that light. On Mars, now we haven't stood on Mars yet. Maybe one of you all will. Hey, maybe I will. This is what it looks like in the middle of the day on Mars. It looks like sunset on Earth, because Mars has a different atmosphere. It has an atmosphere. You can see the clouds. Those are water clouds, by the way. But there's no liquid water on the surface of Mars. It's all frozen. The atmosphere here is carbon dioxide. So carbon dioxide plays a different game of pool than nitrogen does with light particles from the sun. It turns out it's exactly the opposite. It's the yellow light that gets scattered from carbon dioxide, scatters yellow light and lets the blue light go through. So what do you think a sunset looks like on Mars, or a sunrise? It's actually blue. We have exactly the same different kind of colors, right? This is because the yellow light is getting scattered, and what's left is coming from the sun is the blue light. Okay, so I think that's it for the oh, it's not it for today. Forgot about that last thing. Which, listen to the high frequency and the low frequency. That's called the Doppler effect. We hear it with sound. We use it for radar to tell when a storm is coming. We use it to, you notice it when a storm is coming. For those of you who live where tornadoes are, when the tornado siren goes on, it's not a constant pitch. It's high pitched when it's moving towards you. When the horn's moving towards you, it's low pitched when it's moving away from you. The wavelength of light gets shifted when an object is moving. So we can tell whether an astronomical object is moving towards us or moving away from us by how the light is shifted. Now, it's not really like the star changes color. I mean, it could if it was going really fast, but what's more happens is the absorption lines move, right? This is how we determine the speed of whether it's coming towards us or away from us, and the Doppler effect is more pronounced the faster an object is moving. So again, if you ever been to a Formula One race or listened to it on watched it on TV, you can really tell the difference of a race car as it's coming towards you or going away from it, even more than the fire engine, because they're moving faster. So this Doppler effect is more pronounced the faster up. So by analyzing the light, we can determine how fast the object is moving and whether it's coming towards us or away from us. When I told you on our first week that the universe was expanding, this is how we know that. We know that the further away a galaxy is, the faster it's going. It's not like we can tell that the galaxies look redder. We can actually see them get a little bit yellower. But scientifically, we just look at their absorption spectrum from the light, and those fingerprints, the relative distances between the bands stay the same, but the whole thing just gets shifted over. Right, this one got shifted so much we lost this first band there. Okay, all right, so that is it for today. I will let me get out of this and see if we have any questions or comments. So is that clear to everybody? Cool. All right. Well, thanks for joining, and I will I'll speak to you all in the discussion questions, and we'll have another virtual class on Wednesday. Keep up the great work. You all are doing fantastic. Stay strong and stay healthy, and be safe. I'll talk to you later. Bye.
You are currently the only person in this conference.